You glance at the moon through your window. It is there, pale, round, entirely settled, hanging in the dark whether you notice it or not. That is not a philosophical gamble. It is just how the world works. Objects exist. They sit where they are. Looking at them tells you what was already true. This is the foundation of every waking moment, and no sensible person doubts it. But in 1961, a Hungarian-American physicist named Eugene Wigner, who had already won the Nobel Prize and helped build the atomic bomb, followed one line of quantum reasoning to a conclusion that unsettled even him. He argued, in complete seriousness, that reality does not settle into a single definite outcome until a conscious mind registers it. Not a detector, not a machine, a mind. And he did not argue this casually. He built a thought experiment, now called Wigner's friend, to show why he thought quantum mechanics could not be stated consistently any other way. Then, quietly, over the next 2 decades, Wigner changed his mind. What counts as looking? And why, when you finally do look, do you only ever see one thing happen? The first person to notice the problem was not Wigner. It was John von Neumann, a mathematician so formidable that his colleagues joked he was not quite human. In 1932, in Berlin, von Neumann published the book that gave quantum mechanics its modern mathematical skeleton, a rigorous formalism that physicists still use today. Buried in that formalism was a puzzle that would haunt the field for the next century. Von Neumann showed that quantum mechanics runs on 2 rules. The first rule, which he called process 2, says that when you are not looking, a quantum system evolves smoothly, continuously, deterministically, according to the Schrödinger equation. The system can hold multiple mutually exclusive possibilities at once, a state called superposition. A particle can be here and there simultaneously. A photon can take 2 paths at once. The possibilities do not cancel each other out. They coexist, interfere, combine. The second rule, process 1, says that when you measure, you get exactly one definite outcome, chosen with a certain probability, and the other possibilities simply vanish. The wave function, as physicists say, collapses. These 2 rules are not remotely alike. One is smooth and deterministic. The other is abrupt and random. One allows many things at once. The other gives you exactly one. And nothing in the smooth rule tells you when or why the abrupt rule takes over. That gap is the measurement problem. It is not a problem of technology or precision. It is a problem of logic. The theory does not say where the boundary is. Von Neumann then proved something even stranger. He showed that the boundary between the quantum system and the classical measuring device, the place where the collapse supposedly happens, can be drawn anywhere along the chain, and the predictions stay identical. You can say the collapse happens in the particle, or in the detector that catches it, or in the pointer that swings, or in the light that bounces off the pointer, or in the retina of the observer, or in the optic nerve, or in the brain. The physics is unchanged. The boundary, von Neumann wrote, is arbitrary to a very large extent. It is a choice, not a fact. You can keep describing everything quantum mechanically, particle, detector, pointer, photons, retina, nerve, and the Schrödinger equation never forces you to stop. The collapse never has to happen. This movable boundary is now called the Heisenberg-von Neumann cut, and it is the seed of the whole story. Because if the cut is arbitrary, and you can keep pushing it back indefinitely, then what actually ends the chain? And what forces just one outcome to become real? Von Neumann did not answer that question. He left it open. But the fact that he could push the boundary all the way to the observer planted an idea that would not go away. Maybe the observer is not just where you happen to stop describing things quantum mechanically. Maybe the observer is where the collapse genuinely occurs. Eugene Wigner picked up that thread 3 decades later. Wigner was Hungarian, like von Neumann, and the two had known each other since their days in Europe. Both had fled to America in the 1930s. Wigner worked on the Manhattan Project, won the Nobel Prize in 1963 for his contributions to nuclear and particle physics, and by then ranked among the most respected theoretical physicists alive. He was not a mystic, he was not careless, and in 1961, in an essay published in a volume called The Scientist Speculates, he made the case that quantum mechanics could not be formulated consistently without reference to consciousness. His reasoning was straightforward. If you take the quantum formalism seriously, and you follow von Neumann's insight, then you can describe an entire laboratory, the experiment, the apparatus, the detector, the readout, as a single quantum system, and that system can sit in a superposition of outcomes. Nothing in the mathematics stops you. But then, Wigner asked, what about the scientist inside the laboratory? Suppose a colleague of yours, your friend, is sealed in a lab running an experiment. The experiment has two possible results, a flash of light or no flash. Your friend looks at the detector and sees one or the other. To your friend, the result is definite. They saw the flash or they did not. But you, standing outside the lab, can describe the entire lab, including your friend, as a quantum system. And according to the Schrödinger equation, that system sits in a superposition. Flash and friend saw it, plus no flash and friend saw nothing. Both at once. Your friend, in this description, does not yet hold a definite memory. They hang suspended between the two possibilities. Then you open the door and ask your friend what happened. They answer immediately, with certainty, that they saw the flash. No hesitation, no doubt. They had a definite experience the moment they looked, long before you asked. So which description is correct? Did the outcome become definite when your friend looked, or only when you asked? Wigner found the second option absurd. He wrote that describing the friend as suspended in superposition implies that my friend was in a state of suspended animation before he answered my question. The friend's testimony, their plain insistence that they knew the answer all along, seemed to rule out the idea that they had ever been in a superposition. And if the friend's consciousness is what collapses the wave function, then consciousness is not just a passive receiver of information. It is the thing that makes reality definite. Wigner concluded that it was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to the consciousness. Here is the strange part. Wigner was not saying that consciousness changes the outcome, like telekinesis. He was saying that consciousness is what turns a spread-out cloud of possibilities into a single, settled fact. Before the friend looks, the flash is neither there nor absent. It is both in superposition. When the friend becomes aware of the result, the superposition collapses and one outcome becomes real. The friend does not choose which outcome. But without the friend's awareness, Wigner argued, there is no outcome at all. And that leads to a question that sounds like philosophy but is actually physics. What counts as awareness? Does it need to be human? Could a cat do it? Could a bacterium? Could a very sophisticated detector? Wigner did not have a crisp answer. He suspected that consciousness was something distinct from physical processes, something that could not be reduced to neurons and electricity. He wrote, carefully, that solipsism may be logically consistent with present quantum mechanics, but materialism, the idea that everything, including the mind, is just physical stuff, is not. He knew how this sounded. He knew it opened the door to questions he could not answer cleanly. But he could not see another way to stop the infinite regress, the endless chain of detectors observing detectors. At some point, he thought, you need something that is not just another quantum system. You need an observer who genuinely holds a perspective, who genuinely experiences one outcome and not the other. And the only candidate he could find was consciousness. Why does this matter? Because Wigner's reasoning was not fringe speculation. It was a rigorous attempt to take the formalism of quantum mechanics seriously, and it forced physicists to confront a question they had been quietly avoiding. If the collapse is real, What causes it? And if it is not real, then what are we actually measuring? For a few decades, Wigner's view held a foothold. It was not popular, but it was not dismissed outright. Other physicists, like Fritz London and Edmund Bauer, had floated similar ideas in 1939, though they had been more cautious. Wigner went further. He made the claim explicit, and he gave it a name: the consciousness causes collapse interpretation. But even as he published it, the ground was shifting. Around the same time, a handful of physicists were beginning to realize that the environment, the uncontrolled, unobserved surroundings of any real system, might do the job that Wigner thought required a mind. And if they were right, then consciousness was not special at all. The person who saw it first was a German physicist named Heinz Dieter Zeh. In 1970, in Heidelberg, Zeh wrote a paper with a simple but radical idea. He proposed that a quantum system, when it interacts with its environment, the air, the photons bouncing around the room, the thermal vibrations of nearby atoms, becomes entangled with that environment so quickly and so thoroughly that the interference between the system's superposed states is destroyed for all practical purposes. The system still obeys the Schrödinger equation. There is no collapse, no new law. But the information about which outcome occurred leaks into so many environmental degrees of freedom that you can never gather it back. The superposition is still there, in principle, but it is irreversibly smeared across trillions of particles. For any observer confined to the system, the superposition is gone. This process is now called decoherence, and it is the single most important discovery in quantum foundations since the 1930s. But in 1970, almost no one wanted to hear it. Zeh had enormous difficulty getting the paper published. The journal that eventually accepted it, Foundations of Physics, was brand new. Referees were hostile. Colleagues dismissed the idea. Zeh later recalled that he had to be strategic. He advised his doctoral student, Erich, Joos, to study the effect of the environment on a quantum system without ever talking about Hugh Everett's many worlds interpretation, which was still considered too speculative. Focus on the reduced density matrix, Zeh told him. Focus on the mathematics. This was something nobody could deny. And it worked. In 1985, Zeh and Joos published a landmark paper calculating how fast decoherence happens for various systems. The numbers were staggering. Consider a dust grain, a tiny speck, barely 1/100th of a millimeter across. Suppose it is floating in deep space, in perfect vacuum, with no starlight nearby. The only thing touching it is the cosmic microwave background, the faint leftover glow of the Big Bang, which fills the entire universe at a temperature of roughly 3 degrees above absolute zero. Even in that nearly empty void, with nothing but ancient photons brushing against it, the dust grain decoheres in about 1 second. 1 second. If you could somehow prepare the grain in a superposition of being here and there, separated by its own width, that superposition would be effectively erased in the time it takes you to blink. And that is in the most isolated environment imaginable. On Earth, in air, at room temperature, a dust grain is struck by roughly 10 billion photons every second from sunlight alone, not counting air molecules. Decoherence happens so fast that the timescale is essentially unmeasurable. Joos and Zeh estimated it at something like 10 to the minus 31 seconds for a grain in air. A trillionth of a trillionth of a trillionth of a second. For a 1 gram object in a superposition of 2 positions separated by 1 centimeter, the decoherence time at room temperature is about 10 to the minus 23 seconds. That is 100,000th of a billionth of a billionth of a second. Far, far shorter than any apparatus could ever resolve. The environment is always in the room. It is always watching. And it collapses the appearance of quantum behavior long before any human or any conscious mind shows up. This is the mechanism Wigner did not have. Decoherence explains why we never see macroscopic objects in superposition, why pointers point one way and not 2 ways at once, why Schrödinger's cat is never both alive and dead in any observable sense. It does all of this without invoking consciousness, without requiring a special observer, and without adding any new laws to quantum mechanics. The environment selects a preferred set of states, called pointer states, that are stable against entanglement. Position is a pointer state, momentum is not. That is why we see objects in definite places, not definite momenta. The selection is not arbitrary, it is determined by the way the system couples to its surroundings, and it happens automatically, everywhere, all the time. The cosmic microwave background has been doing this to dust grains for 13 billion years, long before any eye or mind existed anywhere in the universe. That fact alone is enough to cast serious doubt on Wigner's view. If the wave function waited for a conscious observer to collapse it, then what was collapsing dust grains for eons before life arose? Did the universe sit in a vast superposition, holding all possible configurations at once for billions of years until a single-celled organism appeared? And even then, does a bacterium count? Does it need a nervous system, a cortex, a sense of self? Where exactly do you draw the line? The physicist John S. Bell, in a 1990 essay titled Against Measurement, put the objection more sharply. He asked, was the wave function of the world waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? The sarcasm was deliberate. Bell was pointing out that if you make consciousness the trigger for collapse, you have to say which kind of consciousness, and any answer you give will sound arbitrary. A human with a PhD has no deeper access to quantum reality than a dog or a worm. And a worm has no access that a virus does not. The line keeps retreating, and there is nowhere stable to put it. Wigner knew this. By the early 1980s, he had read Zeh's work and the follow-up papers by Wojciech Zurek and Erich Joos, and he changed his mind. In a lecture in 1982, he described his earlier view as a form of solipsism and said he could no longer hold it. In 1984, he wrote plainly that the argument which convinced him that quantum mechanics has narrower limits, that it does not apply without modification to macroscopic bodies, was due to Zeh. He did not make a public spectacle of the reversal. He simply stopped defending the consciousness interpretation and moved toward a different view. That quantum mechanics itself might need modification at large scales, that there might be an objective, physical collapse mechanism with nothing to do with observers. He never pinned down what that mechanism was, but by the mid-1980s, other physicists were starting to propose candidates. In 1986, 3 Italian physicists, Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, published a model in which every particle, at random, spontaneously localizes in space at an extraordinarily low rate. For a single particle, the collapse rate is about once every 100 million years. But for a macroscopic object made of 10 to the 23 particles, the collapses add up, and the object localizes about 10 million times per second. The collapse is not triggered by observation. It just happens, spontaneously, as a fundamental process of nature. The model is called GRW, after its authors, and it has been refined and tested ever since. It makes predictions. It can be falsified. And that, in a way, is its greatest virtue. It is not philosophy. It is physics. But does decoherence actually solve the measurement problem? It depends on what you mean by solve. Decoherence explains why macroscopic superpositions vanish for all practical purposes. It explains why we never see pointers in 2 places at once, why laboratory experiments give definite results, why the world looks classical. It does all of this beautifully, and every calculation agrees with experiment. But decoherence does not, by itself, select which outcome occurs. It explains why you will see the pointer pointing left or pointing right, never both. It does not explain why, in this particular run of the experiment, you see left and not right. The probabilities are still there, given by the quantum state, but decoherence does not pick the winner. Physicists call this the problem of outcomes, and it is still open. Some physicists, following Hugh Everett, say there is no problem because all outcomes happen. The universe branches and both versions of U exist, each seeing one result. The probabilities, in that view, describe the weights of the branches, not the chance of ending up in one. Other physicists, following the GRW model and its descendants, say there is a genuinely random, objective collapse, and it happens whether or not anyone is watching. Still others, following the Copenhagen interpretation, say the wave function is not a real thing, but a catalogue of what we can predict, and collapse is just the updating of that catalogue when we learn something new. And a smaller group, following the pilot wave theory of Louis de Broglie and David Bohm, say the particles always had definite positions, guided by a real wave we never directly see, and there is no collapse at all. None of these interpretations has won. Polls of physicists, when they are taken, show no consensus. A survey in 2013 of 33 participants at a Foundations conference found that 42% favoured some version of the Copenhagen interpretation, 24% favoured information-based or Bayesian views, and not a single participant endorsed the pilot wave theory. But the sample was small, and the results were all over the place. The Nobel Committee, in 2022, awarded the prize to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons that ruled out local hidden variable theories and opened the door to quantum information science. In the announcement, a member of the committee said the laureate's work has also shaken the very foundations of how we interpret measurements. A century after the theory was written, the people who understand it best still argue about what it means. So where does that leave Wigner's friend? As it turns out, the friend is not done. In the last decade, a new generation of physicists has taken Wigner's thought experiment and made it empirical. Not with a real person in a lab, that is still impossible, but with photons and qubits playing the role of the friend. In 2019, a group led by Massimiliano Proietti and Alessandro Fedrizzi at Heriot-Watt University in Edinburgh built an experiment involving 6 entangled photons, arranged to encode 2 friends and 2 superobservers. Each friend measures a photon, recording a definite result. Each superobserver then performs a quantum interference measurement on the entire friend plus photon system, treating the friend as still in superposition. The setup lets you test whether the 4 observers, 2 friends and 2 superobservers, can assign consistent facts to the same events. And the experiment showed, with 5 standard deviations of confidence, that they cannot. The observers, following quantum theory correctly, are driven into contradictory statements. One observer says the result is definite. Another, treating the whole lab as quantum, says it is still in superposition. Both descriptions are valid within quantum mechanics, but they cannot both be true in any absolute sense. The measurement value was S equals 2.416, derived from 1,794 6-photon coincidences collected over 360 hours of running. The experiment did not prove that consciousness collapses the wave function. The friends in this case were single photons, not minds. What it did prove is that quantum mechanics does not support the idea of observer-independent facts, facts that are true for everyone, regardless of which measurement they perform. And that conclusion has been sharpened by a series of recent no-go theorems with names like local friendliness, absoluteness of observed events, and the frauchiger-renner paradox. All of them say, in different ways, that if you take quantum mechanics seriously and apply it to observers themselves, you are forced to give up something. Either locality, or the idea that measurement outcomes are absolute, or the assumption that a single quantum state describes the whole system. You cannot keep everything. Think about what that means. The original puzzle was this: does looking at the moon make it real? And the honest answer, after a century of work, is more subtle than either yes or no. Looking does not create the moon. The moon was there, scattering sunlight and pulling the tides long before any eye opened. But the question of what was true before you looked, whether the particle was here or there, whether the photon took this path or that, turns out not to have an observer-independent answer. The measurements you choose, the systems you treat as quantum versus classical, the boundary you draw between observer and observed, all of these affect what you can consistently say happened. Local realism, the idea that objects carry definite properties independent of measurement and that information does not travel faster than light, is experimentally false. That was settled in 2015 in 3 separate laboratories with every known loophole closed. At Delft University of Technology in the Netherlands, Ronald Hansen and Bas Hensen used electron spins trapped in nitrogen vacancy centers in diamond, separated by 1.3 kilometers, and measured a violation of the Bell inequality with a statistical confidence such that the probability of the null hypothesis was at most about 4%. At NIST in Boulder, Colorado, Krista Shalm and Se-Woo Nam used photons in 2 rooms 185 meters apart and closed the detection loophole with superconducting detectors, efficient enough that they could no longer blame losses for the correlation. At the University of Vienna, in the sub-basement of Hofburg Castle, Marissa Justina and Anton Zeilinger ran a similar test with detectors 60 meters apart. All 3 saw the same thing. Nature violates the bounds that local realism requires. The correlations are stronger than any local hidden variable theory allows. The Nobel Prize in 2022 went to Aspect, Clauser, and Zeilinger for making that case airtight over 4 decades of work. But those experiments do not tell you which interpretation is correct. They rule out one class of interpretations and leave the rest standing. Decoherence explains why the world looks classical and why we never see macroscopic superpositions. It does not pick the outcome. Many worlds says all outcomes are real. Objective collapse says one outcome is selected at random by a new physical process. Pilot wave theory says the particle always had a path, and the wave just guides it. Cubism says the wave function is personal, a bookkeeping tool for agents, and collapse is updating your information. Relational quantum mechanics says outcomes are relative to observers, and there are no absolute facts. All of these survive the Bell tests. None of them has been ruled out by experiment. And consciousness causes collapse, the view Wigner held and then abandoned, is still on the list, though now as a minority position, and one that Wigner himself decided was a mistake. Here is what experiment has actually shown. Quantum interference is real. Superpositions are real. You can put molecules containing 2,000 atoms into a superposition of passing through 2 places at once, and when they arrive at a screen 2 meters away, they form an interference pattern that could only happen if each molecule went both ways. The experiment was done in Vienna in 2019 by Marcus Arndt's group using a sophisticated interferometer with a baseline longer than most dining tables. The molecules were porphyrins and other large organic compounds, with masses above 25,000 daltons, held in a beam and sent through a series of gratings. The interference fringes appeared exactly as predicted. These are not clouds of uncertainty. They are real objects with hundreds of atoms apiece, and they interfere with themselves. Decoherence is real. It has been calculated, measured, and confirmed in system after system. The timescales match the theory. A dust grain in air decoheres in a time far too short to measure. A dust grain in the cosmic microwave background decoheres in about a second. A 1-gram object in a superposition separated by a centimeter decoheres in about 10 to the minus 23 seconds. The environment is always watching, and it does not need eyes. The Bell inequality violations are real. Loophole-free tests with space-like separated measurements and high-efficiency detectors have been done not just with photons but with atoms, ions, and superconducting circuits. In 2023, a group at Zurek, led by Andreas Wallraff, ran a loophole-free Bell test using superconducting qubits, artificial atoms made of aluminium on a chip, separated not in space but in time, using a clever protocol that closed the locality loophole by making the measurement choices after the entanglement was created. The violation held. The objectivity of observed events is not real, or at least not in the sense we thought. The Wigner's friend experiments and the no-go theorems show that you cannot consistently maintain that all observers agree on what happened. If you treat an observer as a quantum system, then to someone outside, that observer can sit in a superposition of having seen two different outcomes. Both descriptions are mathematically valid. They just cannot both be absolutely true. And objective collapse models are being cornered. In 2020, a team led by Sandro Donardi and Angelo Bassi, working at the Gran Sasso National Laboratory in Italy, under roughly 3,000 meters of rock, searched for the faint X-rays and gamma rays that would be emitted if gravity were spontaneously collapsing wave functions, as proposed by the diosi-penrose model. They found nothing. The null result ruled out the simplest parameter-free version of the model and set a bound about 3 orders of magnitude tighter than before. One of the co-authors on the paper was Lajos Diosi, one of the model's own architects. The fact that he participated in constraining his own theory is a quiet testament to how science is supposed to work. Other experiments are squeezing the parameter space further. Molecular interferometry pushes the mass limit higher every few years. Levitated optomechanics, trapping tiny glass beads in laser light and cooling them to near their quantum ground state, is approaching the regime where collapse models predict a detectable signal. Space-based experiments, like LISA Pathfinder, have tested gravitational collapse proposals by looking for anomalous noise in free-falling test masses. The data so far favor standard quantum mechanics with decoherence, not objective collapse. But the models are not dead. They are falsifiable, and they are being tested. That is more than most interpretations can claim. So, here is where we stand. Consciousness does not cause collapse. That is the mainstream view, and it is the view best supported by the evidence. Decoherence explains why the world looks classical, why we see definite outcomes, and why the boundary between quantum and classical is not a sharp cut, but a continuous transition that happens automatically when a system becomes entangled with a large environment. The environment is doing the job Wigner thought required a mind, and Wigner himself, after reading the decoherence work by Zeh and Zurek, concluded he had been wrong. That is not a footnote, that is the arc. But decoherence does not select which outcome occurs. It explains the appearance of collapse, not collapse itself. And quantum mechanics, after 100 years, still does not tell us why, when you look, you see this and not that. The interpretation you prefer determines how you answer. If you are an Everettian, all outcomes happen and the question is meaningless. If you follow GRW or a similar collapse model, the outcome is selected by a genuinely random, objective process built into the laws. If you follow Copenhagen, the wave function is not real, and collapse is just updating your knowledge. If you follow Bohmian mechanics, the particle always had a position and the wave just guided it. If you follow cubism, the wave function is personal and collapse is subjective. If you follow relational quantum mechanics, there are no observer-independent facts, and every outcome is relative to a reference frame. And if you still, against the weight of everything, hold to consciousness causes collapse, then you have to explain why decoherence looks exactly like collapse without requiring consciousness, and why the cosmic microwave background was collapsing dust grains billions of years before any mind existed. You can hold the view, but you are holding it alone, against the evidence and against the testimony of the one physicist who argued for it most carefully and then changed his mind. There is one thing worth sitting with. The friend in Wigner's thought experiment, the colleague sealed in the lab, looking at the detector, registering a result, genuinely has a definite experience. They saw the flash or they did not. To them, it is not a superposition, it is a fact. And yet to you, standing outside, the formalism says you can describe the whole lab, friend included, as a quantum system in a superposition of both outcomes. Both descriptions are valid, both follow the rules, and both cannot be absolutely true at the same time. That is not a failure of quantum mechanics, that is what quantum mechanics says. The theory works. It predicts everything with stunning precision. But it does not give you a single, observer-independent story about what happened. It gives you different stories for different observers, and those stories do not always align. And when you try to force them to align, when you insist that there must be one objective fact about whether the friend saw the flash, you run into contradictions. The no-go theorems prove it. The experiments confirm it. You cannot have locality, observer independence, and quantum mechanics all at once. Something has to give. Here is the honest edge. A century after quantum mechanics was written down, after decoherence has beautifully explained why the world looks classical, after the Bell tests have ruled out local realism, after molecular interferometry has pushed superpositions to thousands of atoms, after the Wigner's friend experiments have empirically tested observer dependence, physics still has no agreed account of why a single definite outcome occurs at all. Not how the world looks classical, why in this run you saw this. The problem of outcomes is still open. The measurement problem is still open. The interpretation question is still open. Wigner thought consciousness was the answer and then decided it was not. Zeh and Zurek thought decoherence dissolved the problem. Bell thought the problem was the theory itself and that we needed a better one. Everett thought there was no problem because nothing collapses. Girardi, Rimini and Weber thought the collapse is real and spontaneous. And after decades of argument and experiment, no view has won. The theory that built the modern world, that powers every computer and laser and MRI machine, that predicts the spectrum of hydrogen to 15 decimal places, does not tell you what happens when you look. It tells you what you will probably see. It does not tell you why you see one thing and not the other. And it does not tell you whether the thing you see was already true before you looked, or whether the looking had something to do with making it true. The moon is still there when you turn away. Decoherence guarantees it. The environment has already measured it 1 billion times over. But the question Wigner raised, the question von Neumann planted by showing the cut was arbitrary, is not about the moon. It is about the boundary between what is and what might be, and about where that boundary sits, and about whether it sits anywhere at all. Quantum mechanics is silent on that. It gives you rules for calculating probabilities, and the probabilities are perfect, but it does not give you a picture. And every attempt to force a picture, to say this is what is really happening, leads to a different interpretation, and none of them has been ruled out. So the moon is there, the dust grain is there, the photon went through the interferometer, and the question of what was true before you checked, and why you see what you see and not the other thing, is still the most interesting open question in physics. Not because we lack data, because we lack agreement on what the data means. Wigner asked what ends the chain. We still do not know. And that not knowing, that unbridged gap in the center of the most successful theory ever written, is the most honest answer anyone can give. If you like understanding things this way, if you want the clearest version of the science and the most honest version of the edge, then subscribe. We will keep finding the questions that matter and the answers where they exist, and the places where the answers stop. Stay curious. The experiments that proved local realism is false did not happen overnight. They took 40 years of grinding technical work, and the story of how the loopholes were closed is worth sitting with. When John Bell published his theorem in 1964, he showed that any theory in which particles carry pre-existing local properties, independent of measurement, must obey a certain mathematical inequality. Quantum mechanics predicts that inequality will be violated, so the question became empirical. Does nature obey the inequality or violate it? The first test was done in 1972 by Stuart Friedman and John Clauser at the University of California, Berkeley. They used calcium atoms excited to emit pairs of photons in opposite directions, with polarizations that quantum mechanics said should be correlated in a way no local hidden variable theory could match. They measured the correlations and found a violation, but the experiment had gaps. The detectors were not efficient enough to catch every photon, so you could not rule out the possibility that the photons you missed were the ones that would have restored the inequality. That gap is called the detection loophole, and the polarizer settings were fixed ahead of time, so in principle the photons could have known which measurements were coming and adjusted their behavior accordingly. That gap is called the locality loophole. For decades, every Bell test had at least one loophole open. Some closed the detection loophole but not the locality loophole. Others closed the locality loophole but not the detection loophole. And critics, fairly, pointed out that you could not claim to have definitively ruled out local realism until you closed both at once. Alain Aspect, working in Orsay, France, made the first major step in 1982. He built an experiment in which the choice of which polarization to measure was made while the photons were in flight, using a switching mechanism so fast that no signal traveling at the speed of light could inform one photon of the measurement choice made on the other. The correlations still violated the inequality, but the detection efficiency was still too low, so the detection loophole remained. It took another 33 years to close both loopholes simultaneously. The breakthrough came in 2015. And it came in 3 different labs within a span of a few months, as if the technology had finally matured all at once. At Delft, the system was not photons, but electron spins trapped in nitrogen vacancy centers inside diamond crystals, separated by 1.3 kilometers of optical fiber running under the streets of the city. The team, led by Ronald Hansen, used a clever protocol in which a photon emitted by one electron was sent to a beam splitter halfway between the 2 labs, and the detection of that photon heralded the creation of entanglement between the 2 distant electrons. Then, within a microsecond, while the entanglement still lived, each lab made a random measurement on its electron. The measurement choices were made by random number generators, and the settings were locked in only after the entanglement was created, so there was no time for any signal to pass between the labs. The electrons had no way to know what was coming. The detectors had high efficiency. Every loophole was closed, and the inequality was violated. The measured value of the CHSH parameter was 2.42, plus or minus 0.20. The classical bound is 2. Quantum mechanics predicts a maximum of about 2.82. The Delft result sat comfortably in between, far enough from 2 to rule out local realism with a probability of the null hypothesis at most about 4%. That is not 5 sigma, the gold standard in particle physics, but it is well beyond reasonable doubt. Christa Schalm, working at NIST in Boulder, used photons but with superconducting detectors efficient enough to close the detection loophole. And he placed the detectors in 2 rooms far enough apart, 185 meters, that the measurement choices could be made independently in the brief time the photons were in flight. Schalm later recalled the pressure. They needed the fiber coupling efficiency up above 95%, and they were worrying about every 0.25%. The experiment worked. The inequality was violated. At Vienna, Marissa Justina and Anton Zeilinger ran a similar test in the sub-basement of Hofburg Castle, with detectors 60 meters apart, and saw the same violation. All 3 results were published in 2015. All 3 closed the loopholes, and together they settled the question. Local realism is false, not probably false. Not false within some interpretation. false, period. Nature does not behave as though particles carry definite local properties independent of measurement. The correlations are real, they are stronger than locality allows, and there is no way to explain them with hidden variables unless you give up either locality or some other foundational assumption like free choice or statistical independence. The 2022 Nobel Prize went to Aspect, Clauser, and Zeilinger for that body of work. The citation said the prize was for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Eva Olsen, speaking for the Nobel Committee, said the laureate's work has also shaken the very foundations of how we interpret measurements. That last phrase is important. The experiments do not tell you which interpretation is correct. They tell you that whatever interpretation you choose, it cannot be a local realistic one. The universe is either non-local, meaning that measurement outcomes at one location can depend on measurement choices made far away, faster than light could travel between them, or it is not realistic, meaning that particles do not carry pre-existing values for every observable. Or possibly both. Quantum mechanics itself does not pick sides on that question. It just says the correlations will be there, and they are. But each interpretation handles the correlations differently. In the Everett picture, all outcomes happen and the branches decohere from one another so fast that you never see the other branch, but both are real, and the correlations are just correlations between branches. In the pilot wave picture, the particle always has a definite position, guided by a real non-local wave, and the correlations come from the wave instantly adjusting across space. In the Copenhagen picture, there are no values until you measure, and the correlations are irreducible features of the quantum state. In objective collapse models, the collapse is random but happens to both particles in a way that respects the entanglement, and the correlations emerge from that. All of these pictures survive the Bell tests. The tests eliminate only one class of explanation, the local hidden variable class, and they do it decisively. What they leave behind is a menu of strange options, none of them comfortable, all of them still on the table. And then, starting around 2018, a new round of no-go theorems appeared, and they tightened the constraints even further. The frauchiger-renner paradox, published in Nature Communications in September 2018, showed that if you apply quantum mechanics to observers themselves, and you assume that an observer's measurement has a single definite outcome that every other observer can agree on, and you assume consistency across time, then you can construct a scenario in which two observers, both reasoning correctly, reach contradictory conclusions about what happened. The scenario involves two labs, each containing an agent who makes a measurement and records a result, and two super-observers, each of whom treats an entire lab as a quantum system and performs an interference measurement on it. The setup is intricate, but the conclusion is sharp. You cannot have all three. Single-world quantum mechanics, observer-independent facts, and logical consistency. Something has to give. A few months later, Czesław Bruckner, working in Vienna, published a related no-go theorem showing that you cannot maintain that observed events have objective, observer-independent outcomes if you want to preserve locality and the freedom to choose measurements. The theorem applies to extended Wigner's friend scenarios, and it rules out what Bruckner called observer-independent facts. Not the facts themselves, but the idea that every observer must agree on them. Then, in 2020, Kokwei-Bong, working with Howard Wiseman and others, published a theorem they called local friendliness in nature physics. The theorem starts from three assumptions. First, absoluteness of observed events, meaning that once an observer has seen an outcome, that outcome is an objective fact for everyone. Second, locality, meaning that an observer's choice of measurement does not affect distant outcomes faster than light. Third, no superdeterminism, meaning that measurement settings are free and not conspiratorially correlated with the state being measured. If you assume all three, Bong showed, you can derive an inequality, much like a Bell inequality, that quantum mechanics violates in extended Wigner's friend scenarios. So at least one of the three assumptions must be false. Either observed events are not absolute, or locality fails, or the freedom to choose measurements is illusory. The paper included an experimental proposal, and within months, several groups built versions of the experiment using entangled photons to encode the friends and superobservers. One of those experiments was the 6-photon setup by Proietti and Fedrizzi mentioned earlier. Another was done by a group in China. Both saw violations of the inequality. The observed events are not absolute. That is the conclusion with the least philosophical cost, and it is the one most physicists have accepted. What it means, concretely, is that when your friend inside the lab measures the photon and sees a definite result, that result is real and definite for your friend. But to you, standing outside and treating the whole lab as a quantum system, the friend sits in a superposition of having seen both possible results. Both descriptions are valid. Both are consistent with quantum mechanics. They just describe the situation relative to different observers, and there is no overarching, observer-independent fact that settles which one is the true description. Facts, in this view, are relational. They depend on your reference frame, much like simultaneity in relativity depends on your reference frame. Two events that are simultaneous in one frame are not simultaneous in another, and there is no absolute sense in which one frame is right and the other wrong. Similarly, an outcome that is definite relative to one observer may still sit in superposition relative to another, and there is no absolute sense in which the outcome has or has not occurred. This is a genuinely strange picture, and it takes time to sit with. Think about a courtroom. A witness testifies that they saw the defendant at the scene of the crime. That testimony is a fact. It happened. The witness holds a definite memory. But now suppose a superobserver, capable of treating the witness and their entire brain as a quantum system, performs an interference measurement and shows that, relative to them, the witness sits in a superposition of having seen the defendant and not having seen the defendant. Both descriptions are valid. The witness's memory is definite to the witness, but indefinite to the superobserver. There is no contradiction because the two descriptions are relative to different reference frames, different levels of access to the system. In practice, of course, no superobserver can do this to a human brain. The decoherence is far too strong, the number of particles far too large. But the formalism says it is possible in principle, and the experiments with photons confirm that the formalism is right. The friend's definite result is real for the friend, and the superposition is real for the superobserver, and quantum mechanics does not force them to agree. What it forces them to agree on is the statistics. If the superobserver later asks the friend what they saw, the friend will give a definite answer, and the probability of that answer matches what quantum mechanics predicts. But until the superobserver asks, the friend's state, from the superobserver's perspective, is still a superposition. And the asking itself is another measurement which collapses that superposition from the superobserver's perspective, while leaving open the question of whether something else, even further outside, might still describe the superobserver and the friend together as a superposition. The chain never ends. The cut is arbitrary. Von Neumann was right about that in 1932, and nothing since has changed it. The only thing that has changed is that we now know decoherence explains why the cut appears to sit in a definite place for practical purposes, even though the formalism says it is not. And this brings us back to the question Wigner could not answer. What counts as an observer? In the extended Wigner's friend setups, the friends are photons or qubits, simple quantum systems with two possible states. They are not conscious, they do not have minds, they do not have experiences. Yet the formalism treats them as observers, and the experiments confirm that treating them that way gives the right predictions. So consciousness is not required. A photon can play the role of an observer in the sense that it can become entangled with another system, record an outcome, and decohere into a definite state relative to another part of the environment. That is what an observer is in quantum mechanics. Not a mind, not a conscious being, just a system that interacts, that becomes correlated, that splits off a branch of the wave function. The environment is an observer in that sense. A dust grain is an observer. A photon is an observer. The cosmic microwave background is an observer. None of them need awareness, they just need to interact. And once you see that, the need for consciousness falls away entirely. Wigner thought the chain had to end somewhere, and the only place he could see to end it was at a conscious mind. But decoherence showed that the chain does not need to end, it just needs to branch, and the branches decohere from each other so thoroughly that they might as well be separate worlds. Each branch has its own observers, its own records, its own histories. And each branch is real, at least in the Everett picture, or at least appears real in the decoherence picture, or at least behaves as if it is real in every test we can perform. The difference between those framings is interpretational. The experiments cannot tell them apart. The fact that consciousness is not required does not mean consciousness is irrelevant. We are conscious. We have experiences. Those experiences have a definiteness that the wave function by itself does not provide. You see the pointer pointing left, not a superposition of left and right. You remember having seen it. That memory is a fact about your brain state, encoded in neurons, and it is as definite as anything in the classical world. Decoherence explains why the brain state is definite. The brain is a warm, wet, noisy environment, constantly interacting with itself and with the outside world, and any quantum superposition of macroscopically distinct brain states would decohere in a time so short that it is meaningless to speak of. Your neurons are not in superposition. Your memories are not in superposition. You are not in superposition in any observable sense. But the question of why you have this memory and not that memory, why you saw the pointer pointing left and not right, is not answered by decoherence. It is answered by the probabilities in the wave function, which tell you how likely each outcome was. But it is not answered in the sense of explaining what selected this outcome, what made the universe fall on this branch and not the other. If you are an Everettian, the answer is that the universe did not pick. Both branches are real. You exist in both, and the you in each branch remembers a different outcome. If you follow an objective collapse model, the answer is that a random, spontaneous collapse happened, and this was the result. If you follow Copenhagen, the answer is that the wave function is just a tool for prediction, and the question of what really happened is not a question physics answers. And if you follow the pilot wave theory, the answer is that the particle was always in one place, guided by the wave, and you just did not know which place until you looked. Each answer is self-consistent. Each gives the same experimental predictions, at least within the domains where they have been tested, and none has been ruled out. But one thing is certain: consciousness does not collapse the wave function. The evidence for that is overwhelming. Decoherence happens everywhere, all the time, with or without conscious observers. The cosmic microwave background has been decohering dust grains for billions of years, since long before the first star formed, let alone the first eye. The Earth's oceans have been decohering pebbles on the seafloor since the planet cooled. Photons bouncing off a rock on an airless moon are decohering that rock right now, with no observer within light years. The process is automatic. It is built into the way quantum systems interact with large environments, and it produces exactly the appearance of wave function collapse, the sudden transition from superposition to a definite classical state, without requiring any special role for consciousness. Wigner knew this by the mid-1980s. He read the decoherence papers and he changed his mind. He did not make a public drama of it. He just stopped arguing for the consciousness interpretation and shifted toward the view that quantum mechanics might need modification at macroscopic scales. and the experimental work since then has only strengthened the case. Molecular interferometry has pushed superpositions up to molecules with masses above 25,000 daltons, nearly 2,000 atoms. The Talbot-Lowe interferometer used in the early experiments sent fullerenes, those soccer ball-shaped carbon-60 molecules, through a grating, and they formed interference patterns just as atoms do. By 2013, Marcus Arndt's group in Vienna had demonstrated interference with molecules containing more than 800 atoms. By 2019, they had reached molecules with more than 2,000 atoms, using a technique called LUMI interferometry, which stands for Long Baseline Universal Matter Wave Interferometry. The baseline, the distance between the gratings, was 2 meters, far longer than earlier setups, and the interference fringes were clear. These molecules are not delicate. They are large, complex, stable organic compounds. They have enough atoms to qualify as tiny pieces of matter, not just quantum particles. And yet they interfere with themselves. They go through both slits at once, or rather they exist in a superposition of going through both slits, and when they arrive at the detector, the pattern they form can only be explained if each molecule explored both paths. That is superposition. That is the wave-like nature of matter, and it extends far beyond anything Schrödinger or Heisenberg imagined when they wrote the theory in the 1920s. But here is the limit. These experiments are done in high vacuum, with the molecules flying through at high speed, minimizing their interaction with the environment. Even so, the decoherence is strong enough that the interference pattern washes out if you add too much environmental noise. If you shine a bright light on the molecules, the photons scatter off them and carry away information about which path each molecule took, and the interference disappears. The environment, in effect, measures the molecule, and the measurement destroys the superposition. Not because anyone looked at the scattered photons, just because the photons interacted. The information leaked into the environment, and that was enough. This is the lesson of decoherence, confirmed again and again. You do not need an observer to collapse the wave function, you just need an environment. And the more particles in the environment, the faster the collapse happens. For a molecule in air, the decoherence time is unmeasurably short. For a gram-scale object, it is 10 to the minus 23 seconds. For anything larger, a pebble, a coin, a cat, a person, the decoherence is so complete and so fast that the quantum superposition is gone before it ever had a chance to exist in any detectable way. The world looks classical because the environment makes it classical. Not by observing it in the conscious sense, but by interacting with it in the physical sense. And that happens everywhere, always, with no mind required. Now consider what this means for the original question. You look at the moon and you see it there, round and pale and definite. Was it there before you looked? Yes, in every sense that matters. The moon has been interacting with sunlight, with the solar wind, with cosmic rays, with meteorites, for 4.5 billion years. Every one of those interactions is a measurement in the quantum sense. Every one of them entangles the moon with its environment. The moon's position, its shape, its surface features, all of these have been measured continuously by the environment long before any eye existed. The wave function of the moon, if you want to speak in those terms, collapsed into a definite classical state billions of years ago, and it stays collapsed because the environment keeps measuring it, constantly, with overwhelming strength. The decoherence time for an object the mass of the moon is so short that it is not even meaningful to calculate. It is effectively zero. The moon is classical. It has definite properties. It is there when you look and when you do not. And consciousness has nothing to do with it. The environment did the job. The environment is always doing the job. And that is why Wigner's argument, however carefully constructed, could not survive contact with decoherence theory. The chain does not need to end at a conscious observer. It ends, or rather it branches, at every interaction with the environment. And the environment is everywhere. But Wigner's question is still worth asking, because it exposes a feature of quantum mechanics that is genuinely strange and genuinely unsettled. When your friend looks at the detector and sees a flash, that experience is definite for your friend. They know what they saw. Their brain state encodes the memory. Neurons have fired. Synapses have changed. The information is there, stable, classical, definite. And yet, if you could treat your friend and the entire lab as a closed quantum system, and if you could reverse all the interactions and undo all the decoherence, you could, in principle, show that the friend had been in a superposition all along. You could perform an interference measurement that would reveal that both outcomes, flash and no flash, were still present in the wave function, just decohered into separate branches. You cannot do this in practice. The decoherence is far too strong. The number of environmental degrees of freedom is far too large. The information has leaked into the air, into the walls, into the thermal radiation, into trillions of particles, and gathering it all back is impossible. But the formalism says it is possible in principle. And if it is possible in principle, then the friend's definite memory is not the end of the story. It is definite relative to the friend, but indefinite relative to a sufficiently powerful outside observer. And that is what the Wigner's friend thought experiment is really about. Not whether consciousness matters, but whether definiteness is absolute or relational. The modern consensus, shaped by the no-go theorems and the experiments, is that definiteness is relational. There is no observer-independent fact about whether the friend saw the flash. There is only the fact relative to the friend, and the fact relative to you, and those facts need not agree until you interact and become entangled yourselves. This is not a problem to be solved. This is what the theory says. And the theory works. It has never made a wrong prediction. Every test, every experiment, every technological application, from transistors to lasers to MRI machines to quantum computers, confirms that the theory is correct. So if the theory says that definiteness is relational, then maybe definiteness is relational. Maybe there is no absolute, observer-independent truth about whether an event has happened until that information propagates to you. Maybe the past is not entirely settled, not in the sense of being fixed and definite for everyone, but only in the sense of being definite relative to those who have interacted with it. This is hard to accept because it cuts against every intuition we have. We are built, over evolutionary time, to treat the world as objective and absolute. The rock is there whether you see it or not. The predator is there whether you hear it or not. That assumption is correct for every practical purpose at human scales. But quantum mechanics, applied carefully and honestly, says the assumption is not exactly true. It is approximately true, and the approximation is so good that you will never notice the difference in ordinary life. But at the level of fundamental physics, the assumption breaks. And once it breaks, you are left with a choice of interpretations, none of them comfortable, all of them strange, and none of them ruled out by experiment. You can say all branches are real, and you exist in all of them. You can say there is a random collapse, and this is the branch that survived. You can say the wave function is not real, and the question is meaningless. You can say there are hidden variables guiding everything. You can say facts are relational. All of these are self-consistent. All of them reproduce the predictions of quantum mechanics. And none of them has won. So, where does consciousness fit into all of this? Honestly, we do not know. Consciousness is a real phenomenon. You have experiences. Those experiences have qualities: the redness of red, the pain of pain, the taste of coffee, the feeling of understanding something. Philosophers call these qualia, and they are as much a part of the world as electrons and photons. But physics does not explain them. Physics explains how neurons fire, how signals propagate, how information is processed. It does not explain why any of that feels like something. That is the hard problem of consciousness, and it is genuinely hard. No one has solved it. Some philosophers, like David Chalmers, have argued that maybe consciousness is fundamental, a basic feature of the universe like mass or charge, and that it plays a role in bridging the gap between the quantum and the classical. Chalmers has even revisited the Wigner interpretation, not to endorse it, but to take it seriously as a possibility that cannot be ruled out. He and Kelvin McQueen published a paper in 2021 exploring consciousness collapse theories and arguing that they are not as ill-defined or absurd as most physicists assume. But even Chalmers admits the problems. Defining consciousness precisely is hard. Saying which systems are conscious and which are not is hard. Explaining how consciousness could physically cause collapse without violating known physics is hard. And explaining why decoherence looks exactly like what you would expect if consciousness were not required is very hard. The view is not ruled out, it is just not favored by the evidence. And it is not necessary. Decoherence does the job without it. But there is a residual mystery, and it is worth naming. Suppose you are an Everettian. You believe all branches are real. You believe the universe never collapses, that it just keeps splitting, and that every possible outcome happens in some branch. You exist in all branches. But you, the conscious you reading this sentence right now, only experience one branch. You saw the pointer point left, not right. You remember that. You do not remember the other branch. You do not experience the other branch. Why not? If both branches are real and you exist in both, then why does this instance of you experience only this outcome? The Everettian answer is that there is no mystery, because each branch has its own copy of you, and each copy experiences only its own branch. The branches do not communicate. They decohere from each other so completely that they might as well be separate universes. So the you in this branch experiences this outcome, and the you in the other branch experiences the other outcome, and there is no overarching you that experiences both. But that answer, while self-consistent, does not dissolve the strangeness, it just relocates it. The strangeness is now that there are multiple yous, each experiencing a single outcome, and no meta-you that ties them together. Your sense of being a single continuous self is, in this picture, an illusion. You are a branch, not the tree. And the other branches are just as real, just as much you, even though you will never meet them. Some people find that picture liberating, others find it disturbing, and others find it so ontologically extravagant that they reject it outright. But it is not ruled out, it fits the data, and it solves the measurement problem by denying that measurement is a special process. Measurement is just entanglement, collapse is just decoherence, and the appearance of a single outcome is just the fact that you are confined to one branch and cannot see the others. What about the objective collapse models? These are the theories that say the wave function genuinely, physically, randomly collapses at a low rate for small systems and a high rate for large ones. The most developed is GRW, named after Girardi, Rimini, and Weber. In GRW, every particle, at random intervals, undergoes a spontaneous localization. The particle's wave function, which might have been spread over a large region, suddenly shrinks to a narrow region centered on a random point drawn from the probability distribution given by the wave function. For a single particle, this happens about once every 100 million years on average. So if you have one electron sitting alone in space, you would have to wait roughly the age of the Earth before it spontaneously collapses. But if you have a macroscopic object made of 10 to the 23 particles, then the collapse rate multiplies, and the object collapses about 10 million times per second. Each collapse is tiny, localizing each particle to within about 100 nanometers. But 10 million collapses per second are enough to keep the object in a definite classical state. The object never builds up a macroscopic superposition because the collapses kill it before it can grow. This is an objective process. It has nothing to do with measurement or observation. It just happens, everywhere, all the time, as a fundamental feature of nature. And it makes testable predictions. If GRW is right, then you should be able to see the effects of the collapse in carefully controlled experiments. For example, the collapse should produce a tiny amount of spontaneous heating as the wave function localizes and energy is deposited. And the collapse should show up as a loss of interference in matter-wave experiments when the mass gets large enough. So far, the experiments have not seen either effect. The bounds are getting tighter. The Gran Sasso experiment in 2020 ruled out the simplest version of the diosi-penrose model, which is a variant of GRW where the collapse rate is tied to gravitational self-energy. The experiment looked for X-rays that would be emitted if atomic wave functions were spontaneously collapsing in the way the model predicts. They found none. That does not rule out GRW entirely, because GRW has adjustable parameters, and you can tune them to fit the bounds. But it does rule out the natural, parameter-free version. And every new experiment shrinks the allowed parameter space further. Eventually, if GRW is wrong, the experiments will rule it out entirely. And if GRW is right, the experiments will find it. That is what makes objective collapse models valuable. They are falsifiable. They make predictions that differ from standard quantum mechanics, and those predictions can be tested. Most interpretations do not have that property. The pilot wave theory, also called Bohmian mechanics or de Broglie-Bohm theory, is different again. In this picture, particles always have definite positions. They are never in superposition. What is in superposition is the wave, and the wave is a real physical field that guides the particles. The particle follows a definite trajectory, determined by the wave, and the wave evolves according to the Schrödinger equation. When you measure the particle's position, you just find out where it was, not force it to be somewhere. There is no collapse. The wave does not disappear. It just stops guiding the particle in a way that you can detect. The theory reproduces all the predictions of standard quantum mechanics, and it does so without randomness at the level of individual events. The randomness comes from ignorance of the initial positions, not from indeterminism in the dynamics. But the theory is explicitly non-local. The wave function is defined on configuration space, a space with 3 dimensions for every particle in the universe, and changes to the wave function in one region instantly affect the motion of particles in distant regions. That non-locality is not optional. It is built into the structure of the theory, and it is required to reproduce the Bell inequality violations. The theory does not violate relativity in the sense of allowing faster-than-light signaling, but it does require a preferred reference frame in which the non-local influences propagate. Most physicists find that uncomfortable, and the theory has remained a minority view. But it is not ruled out. It works. It gives the right answers, and it offers a clear, unambiguous ontology. Particles have positions, and the wave guides them. If you want to know what is really happening, the pilot wave theory gives you an answer. The cost is non-locality and a somewhat baroque structure, but the benefit is clarity. Then there is cubism, which stands for quantum Bayesianism. This is a more recent interpretation developed in the early 2000s by Christopher Fuchs, Rüdiger Schack, and David Mermin. The core idea is that the wave function is not a description of the physical system. It is a description of an agent's beliefs about the system. The wave function encodes what you know or what you expect to learn, not what is objectively there. When you measure, you gain information, and you update your beliefs, and the wave function collapses because your state of knowledge has changed. The collapse is not a physical process, it is a Bayesian update. Different agents can assign different wave functions to the same system, depending on what they know, and there is no contradiction because the wave function is personal. It is a tool, not a mirror of reality. Cubism dissolves the measurement problem by denying that measurement is a physical process that needs explaining. Measurement is just an event that happens to you, and you update your expectations accordingly. The theory is provocative, and it has attracted both strong support and strong criticism. Critics say it is too subjective, that it denies the reality of the quantum state, that it cannot explain why different agents' beliefs align so well. Supporters say it is the only interpretation that takes quantum mechanics at face value and does not try to add hidden layers of reality that the theory itself does not require. Cubism is self-consistent. It reproduces the predictions of quantum mechanics, and it has no trouble with the Wigner's friend scenario because it simply says that Wigner and the friend have different information and therefore different wave functions, and there is no need for them to agree until they interact. The view is gaining traction, especially among researchers interested in quantum information, but it remains a minority position. Relational quantum mechanics, developed by Carlo Rovelli in 1996, is similar in spirit but different in detail. Rovelli argues that quantum mechanics is a theory about relations between systems, not about the absolute state of a system in itself. An outcome is definite relative to one observer, but can still be indefinite relative to another, and there is no absolute fact of the matter. The friend has a definite outcome relative to the friend, but not relative to Wigner until Wigner interacts with the friend. This is not subjectivism. The outcomes are real, objective, physical facts, but they are facts about relations, not about intrinsic states. Rovelli draws an analogy to velocity in classical mechanics. Your velocity relative to the ground is different from your velocity relative to a moving train, and there is no absolute velocity. Both are real, both are objective, and there is no contradiction. Similarly, the outcome of a measurement is real and objective, but it is relative to the observer, and different observers can disagree until they interact and align their reference frames. Relational quantum mechanics solves the Wigner's friend problem by embracing the relativity of outcomes. It says the friend's memory is definite relative to the friend and indefinite relative to Wigner, and both descriptions are correct. The theory is elegant, and it fits naturally with the no-go theorems that rule out observer-independent facts. But it is also challenging to formalize fully, and it is not yet clear how it handles all the edge cases, especially when you start stacking observers on top of observers in long chains. The theory is being actively developed, and it may yet become a major contender. And then there is the Copenhagen interpretation, the oldest and still, by some measures, the most popular. Copenhagen is not a single interpretation, but a family of views, loosely associated with Niels Bohr, Werner Heisenberg, and the community of physicists working in Copenhagen.